hand over to Daniel Cronin of the University of Oxford. I must admit, you've defeated me on how to...
Yeah, as you can already tell that I'm the oddball in this lineup by the fact that I'm bringing PDF slides instead of PowerPoint. And that's obviously a naughty thing to do. So let me start with a very brief introduction. So one thing I did want to highlight is that Oxford is a quite major verification center. So I might go as far as boldly stating it's the largest academic place doing verification in the world. So we have 9 full-time academics now working on verification only. And among these 9 full-time academics, we have another 30 plus or so, maybe 40 by now, postdocs, so senior researchers holding a doctorate working on verification as well. So in my group there, right now, I think 10, actually it's 11 now, PhD students or DPhil students, as we would say, and 8 postdocs, and I'm trying to hire 2 more. So the group is funded with about £3 million, and it's really just doing verification. So this mostly comes from industry, in fact, but there's also some funding from Artemis or in the UK that comes from the TSB and various FP7 projects and the like. So my interests are broadly the connection between hardware and software. So I did my PhD on microprocessor verification with FreeImprover, so the really hardcore stuff. And back then we were only dreaming about formal verification becoming automatic, and I guess we can now claim that at least some of this dream has become true. So then moved on towards doing software verification, and I mostly work on the sort of touching point between software and hardware. So, for example, you might have a driver that talks to a piece of hardware, and the driver is the C program, and the hardware is say given in SystemC as a model or an implementation in Verilog RTL. So what I'm going to present today, and it's going to be extremely brief because I'm only getting 20 minutes. I'm not a user, I'm rather a technology provider, but I'm still in the 20-minute time slot category. So what I'm going to talk about is high-level models, and I believe that's something very important to push for. So we have been doing FV for a long time at the gate level, and only now recently the 2 vendors started looking into implementing word-level reasoning technologies. So the buzzwords you might come across is SMT, BB, or that sort of stuff. Until very recently, most of the front ends used by tool vendors in this domain were already bit level in the sense that they would deliver you, even if you give it Verilog RTL, they would deliver you a netlist, and then they would try to do FV on the netlist. So I'm already trying to think 1 step ahead of this. So yes, we need to do word level verification, but we also need to do it at a higher level of abstraction. So if we keep sticking to RTL, and we are missing out scalability opportunities for FV. In particular, we're missing out opportunities for FV to be applied much earlier than it is right now when you have RTL. So the way you could make this happen is by looking at languages like hardware C, spec C, handle C, SystemC, and then you might even have heard that some of these even came out of Oxford from academics from there. So the thing we have in common is that they're based on C and C++, and with this way you hope to be able to push the abstraction level higher, but you also hope to be able to do joint modeling for hardware and software in the same language, as opposed to having a language gap between hardware and software parts. And I think that's extremely important because, especially if you do this in early stages, you might not even have finished your partitioning decision, so meaning you might still be juggling around ideas what to put into silicon and what to put into code. So in this presentation, we're going to focus on SystemC because I think that's the only language that will really become an industry standard in this domain. So that's something based on C++. It's not actually a new language, but it's rather some bunch of macros in the library if you so wish. So this means in order to simulate it, you would not actually buy a simulator, but you would just take an off-the-shelf compiler, get an executable, and run that. Okay. So you still have the usual issues you have with simulation. You still have to feed in test data in order to get some traces and to observe what the system might be doing. So I'm going to be really quite swift with some of these slides, but I'm very happy to provide more detail if anyone is interested. So I did mention that SystemC does offer this idea that you can model both hardware and software with it. And one consequence is that SystemC has maybe rather peculiar semantics when it comes to scheduling and when it comes to concurrency in it. Okay, so what I would want to point out is that SystemC, even though it's a language based on C++, it wouldn't use the same sort of concurrency semantic you would expect from something that you would normally program and then run on an operating system like Linux or Windows. So in Linux or Windows, when you run software in a concurrent fashion, you see asynchronous interleaving semantics, or even worse, you might see weak memory consistency if you use a multi-core target. But in SystemC, in contrast to that, you only have interleaving at very specific locations. So in SystemC, the designer says interleaving happens here or it happens there. So these are designated places, like, for example, when you call the wait function or when you have an end of a thread. Okay? So this has some positive sides. For example, you don't have issues with atomicity. It's very clear what an atomic block is, so it doesn't get interrupted in the middle or anything like this. But then on the negative side, it doesn't really map onto the usual p-thread model. So even though SystemC is a concurrent language, you would, in practice, only execute it on a single core. But this sort of model makes synthesis, in particular, where formal verification much easier, yeah, because you do not have to worry about interleavings within one of these blocks. So this is what this could look like. So, so you might have 3 threads here, and then there is some statements being executed. So you might execute this simple statement: X is 10 here, wait, then do Y is 20, and proceed, right? And then you have these other threads execute and then finish your completion, and then you get some output. Yeah, in this case, we arrive at the state in which X is 11 and Y is 21. But it's obvious there could be an alternative schedule. So the SystemC standard doesn't prescribe particular schedules other than enforced through synchronization constructs. The only thing it requires you is to be consistent. So this means if you run a simulation again, it requires that your simulator produces the same schedule again. But if you use a different simulator or a different version of the same library, you could well get a different schedule. But it's something that's unfortunately quite confusing to many engineers. So particularly you could get this, okay, so you do execute X equals 10 as before, and then you do these 2 other threads, and then you proceed with thread 1, and you could get a different outcome, okay? So this means this is a SystemC program with arrays. This means that the result depends on the schedule. So you could then say, well, let's not write SystemC models with races, but then you will often get the following answer from engineers. They say, we want the races to be there because they model actual potential races in hardware or in hardware-software interaction. And ideally, we would like our simulator to exercise both different schedules so we can see bugs related to those races. Okay? But the SystemC library will do that for you. It will, in fact, try very hard to always execute the exact same schedule, so you won't see any races. Okay? So one response to this that I've seen and actually being used in industry is that people start inserting random delays into their SystemC model in order to make the simulator have different schedules every time you run it. Okay? In contrast to what was intended by the people who came up with the SystemC standard. Okay? So in particular, if you're after a high-level synthesis and you're looking into a simulation synthesis differences, this is a big one. So meaning you run your SystemC simulation, it shows you want a particular result, you run your synthesis, and then fabricate a chip, or you do a RTL level simulation, you get a different outcome, and you would very much like to know why that is the case. Okay? So there are various synchronization constructs that I had mentioned that you can try to make these things go away, but as I said, in many cases, hardware engineers would like to retain non-determinism in their design because this is what is actually reflecting what happens in the chip later on. We won't be building completely deterministic chips in order to make that problem go away. Okay? So this is an example. You might have a FIFO with 2 clock domains. It's meant to be racy. Okay? The race needs to be in the model for it to be proper verification. Okay? And there are many other examples. So buses are very often non-deterministic arbiters and so on. So what I'm trying to come at is some technology that will help hunt schedule-related bugs. So ideally, we want our SystemC simulator to explore multiple schedules to find those schedule-related bugs. And we probably don't want to do the random weights for that. Okay. One reason why this is not particularly promising is that it's very obvious that the number of potential schedules you have to look at is going to grow exponential with the simulation depth. So this means if you want a 100-step simulation, you're looking at 2 to the power of 100 different schedules for that depth. And that's not going to be something very scalable. Okay. So instead of exhaustively trying to enumerate schedules or randomly picking somewhere you hope to get lucky to find something, let's try to explore relevant schedules only. It's clear when you look at those designs, you'll easily find, well, that's a one relevant scenario and that's another relevant scenario. And there are actually not that many relevant scenarios. It's just difficult to know which ones they are, and it's difficult to not miss one. Okay, so what is a relevant schedule? Okay, so if you look at this example again that we had before, one thing that's immediately obvious, if you look at the relative ordering of thread 2 versus thread 3, it's actually pretty irrelevant. Okay, because they write to different variables, in this case x and y, and if you do one before the other, it won't actually affect the outcome. The only thing that's important is how thread 2 and 3 are scheduled with respect to thread 1. That's the important thing, not how they are scheduled with respect to each other. So there's a key observation here, namely that incrementing x and y is commutative. This means you can do it in either order. And so no matter if you do x first and then y, x first and then y, or y first and then x, you will arrive in the final state, which is going to be the same if you start from a common state. So this means you can ignore one of the 2 orders and you still see all the relevant behaviors that you might care about. Okay? And the key thing here is that if you do this systematically, you can often see an exponential number, an exponential reduction in the number of schedules that you have to explore. So there is some formalism behind this, and very well known in the world of software verification. That's called partial order reduction, and it hinges on the definition of 2 threads being independent. I'm not going to go into the details for this. Okay, and so I'm going to skip over that. So there are 2 well-known techniques to make that happen. One is called sleep sets, and the other one is called persistent sets. And it's also well known that these are orthogonal and they can be well combined. So the thing I wanted to point out is that we have an implementation for this for SystemC, and this is a small, tiny SystemC example. And the thing I wanted to point out is that this sort of dependence is obviously something which may depend on control decisions that you're making. Okay, so this is something called a dynamic dependence as opposed to a static dependence. So these 2 threads here, guard and increment. So increment always writes and reads from this variable pressure. Guard reads from pressure, but in only certain cases writes to it. Okay, so it's very easy to see here that these 2 threads are in fact independent, and you could just explore them in a fixed order, save for the one case when you arrive at the maximal pressure. Only then things become relevant. Okay, so meaning at any clock tick that the scheduler processes, you have a choice between first doing guard then increment or increment then guard. And if you exhaustively explore this, then you get an exponential number of schedules for this little tiny stupid program. Okay, but once you realize that there's really only a dependence for this one special case, once pressure reaches Pmax, you can dramatically reduce the number of schedules you're exploring. Okay, and what we are proposing is to use formal verification to detect those dependencies. So take these little blocks, feed them to a formal verification tool, and the formal verification tool will give you a condition under which they can interact with each other. And they use this outcome from the FV tool in order to improve the performance of the simulator. Okay, so I'm using formal verification here to help dynamic verification. And the one key insight here is that the only thing I'm ever doing is taking a block and combining it with another block and checking the interaction between them. I'm never actually applying the formal tool to the full design, and that's important because you know it won't scale otherwise. Okay? So when I'm using that outcome of checking pairs of blocks against each other to do simulation, and the simulator will scale, you know, any size of your system, but this time we'll be doing much more efficient exploration of the schedules. Okay? So this is the final outcome. So if you look at the program that I've shown you before, guard and using this guard and increment threads, what you will find is that these are actually independent in most states. So for example, if you start from a state in which pressure is 0, and the increment then guard, or sorry, increment then guard, then, or alternatively guard then increment, we arrive at a state in which the pressure is going to be 1. With the exception of a state where we are just 1 before Pmax, and suppose Pmax for the sake of this example shall be 10. So if we're in a state where pressure is 9, then suddenly the order matters. Okay? What I'm proposing we do is that we check the value of the pressure. If it's anything less than 9, then don't bother exploring both schedules, just take 1, and we know we will arrive at the same state. If it's 9, then do explore both schedules, and you will expose the bug that this model has, namely that you can exceed the maximal pressure, in fact. Okay? So we have a tool for this, and the tool is called Scoot. It's an analyzing for SystemC model. So let me emphasize, it combines FV and dynamic verification. It uses formal verification to come up which pair of transactions are commutative and under which conditions they are. And then it resynthesizes your SystemC model to obtain a simulator that you will use for dynamic verification. Okay? But it removes in this process enormous overhead because it now knows how transactions interact with each other. And you will see easily a speed up of about an order of magnitude compared to running the original SystemC model. Okay? And we have this available on our webpage. You can download it, play with it, and look at the examples we're providing there. One example is an AS crypto implementation, very standard thing. And if you compare the execution speed, compiling the Scoot output, running that, and compiling the original SystemC model, running that, on the same set of inputs, you see a tenfold increase in performance on a standard Intel machine. Okay? So this is an overview, and with that I will quickly come to an end in order to not have up your schedule. I mean the meeting schedule. Okay? So Scoot reads in a SystemC model, performs all sorts of analyses on this, and this is our expertise to analyze SystemC models. Type checks here, builds control for graphs, does alias analyses, race condition analysis, synthesizes schedulers, and then this code resynthesis, and then it gives you a flat C++ model which you can give to GCC and obtain a simulator which you otherwise can't distinguish from the original SystemC model. Okay? So there's some amount of information I can give you furthermore on experimental results, benchmarks you've done, but I'm going to skip over this. And instead, let me conclude by saying that SystemC, from our perspective, even though it was always meant for simulation, offers great many new opportunities for formal analysis. And in particular, if you're running lots of simulations, it may well be worthwhile that you first perform some heavy static analysis before running your simulations, because you can find out that many things you were going to do during your simulation runs are not actually necessary. You know for sure they're not going to get you to a bug. So I would very much hope to talk to you if you're interested in any sort of co-verification activity, you have drivers, Verilog, or if you're interested in SystemC. Thank you very much.
Thank you. Any questions before? I've got one question. Can this be applied generally to parallelized code rather than just SystemC?
So it does benefit from the fact that this is SystemC, not general parallelized code, because SystemC does have these large block concurrency semantics, right? So if you take very general concurrent code and you were to try to simulate in this fashion, you will find that you have many, many little tiny blocks with potentially many interactions, and the reduction simply won't be that great. You can in principle, but you just don't get that sort of boost as you're getting on SystemC.
One question from James.
So presentation was brilliant. I thought really interesting. So Am I right in thinking that you use commutativity detection to prune down the search space and then you define a schedule as being relevant if it's unique? Is that right, or have I missed something?
Yeah, so we're using exactly commutativity detection to prune down schedules.
Yep.
So you hopefully will arrive at a unique schedule. That would be brilliant because when you do one run and you're done.
Yep.
But in many cases where it might actually be races left that are intentionally in the design and that the designer wants to be there, then you would be exploring only those.
Right.
Okay, and the hope here is that you really only explore those that are important for your designer as opposed to those that are artificially in the SystemC model because you happen to have 1,000 blocks.
Yes.
Right?
Really good. And so I can get this off the web page, and you've got some papers and stuff.
Oh, plenty of papers, and you can get the tool off of that page.
Awesome. Thanks very much.
Are we able to have the slides from today?
Oh yeah, they're on your laptop.
Okay. Oh, okay. Okay.
I won't grab that.
Thank you very much, Tim.
All right, thank you.